Hello, this is Dr. Hanaa Assil, and these are questions and answers on reaction kinetics, which is the first chapter of the IA2 chemistry Edexcel syllabus. So let us take a look at some of these questions and how to answer them. So this is the first question. It says a bromoalkane has the molecular formula C4H9Br. The ionic equation for the hydrolysis of this compound is shown. The rate of hydrolysis was investigated by mixing a large excess of the bromoalkane with aqueous sodium hydroxide and measuring the time taken for all the hydroxide ions to be used up. So this was carried out with different initial concentrations of the bromoalkane and the hydroxide ions, and the results are shown. And the first thing he says is complete the missing value of the initial rate in the table. I'm going to remind you that rate is concentration over time. Now we're talking about what? He's saying the time taken for all the hydroxide ion to be used. So we're going to use the concentration of the hydroxide over the time in the table. So that is the 0.002 over the 35, which is the time for the hydroxide to be used up. And that gives me a value for the rate for that experiment. Remember, rate is concentration over time. Then he says, state the order of the reaction with respect to the bromobutane and to the hydroxide ion. Justify each answer by reference to the concentrations of both reactants. Now, remember that for most of the questions we're going to be talking about, he will give you a table like this where you have different experiments and you are required to determine the order with respect to each of the reactants. So, in order to determine the order with respect to C4H9Br, we choose two experiments in which only the C4H9Br is changing, but the hydroxide remains constant. So, which experiments are we looking at? Experiment 1 and 2, the hydroxide is constant, but the concentration of the bromobutane doubles. Now, what happened to the rate? The rate doubled. We said if the concentration doubles, causing the rate to double, then we're talking about first order. Now, you need to explain why did we say it's first order? Because from experiment 1 to 2, hydroxide ion is constant, the C4H9Br doubles, the rate also doubles. Then we want the order with respect to OH minus. Okay, so we need two experiments again in which the OH minus is changing, but the other one is constant. So we're looking at experiments 2 and 3. Now the C4H9Br is constant. Now the hydroxide, what happened to it? It doubled. Now what happened to the rate? There is actually no effect on the rate, so we say it is zero order. From experiments 2 and 3, the concentration of C4H9Br is constant, the hydroxide doubles, there is no effect on the rate. Now, he's saying write the rate equation. How do we write rate equation? We said the rate is equal to K times the concentration of C4H9Br to the power 1, because we said that's first order. We don't put the hydroxide, or you could put the concentration of hydroxide to the power 0, which really is just 1. Okay, then he says use the results from the first experiment to calculate the rate constant. Now we have written the rate equation, so the rate constant would be the rate over the concentration. Now we choose, he says, for the first experiment. Sometimes he specifies a specific experiment, and sometimes he allows you to choose whichever experiment you like. So here he is specifying the first experiment, so I have to put in the rate for experiment 1 and the concentration of the bromobutane from experiment 1. That gives me a value for K. Now the units, remember we said, how do we write the units? Rate is mole per decimeter cube per second. So I write mole on top, and down I write decimeter cubed second. Now, at the bottom I have concentration, and concentration is mole per decimeter cubed. So mole down and decimeter cubed up. I cancel whatever is the same on the top and bottom of the equation, and that leaves me with just seconds to the -1. What evidence supports the theory that there is more than one step in the reaction mechanism? Of course, the hydroxide is not included in the rate equation, and that means it will come later in the mechanism, and that means it is not in the initial step, or what we call the rate determining step. Write the mechanism for the hydrolysis of the C4H9Br. We just found that it was first order with respect to the bromobutane, zero order with respect to the hydroxide. And we said when we have this kind of rate equation, that means I am starting with a tertiary halogenoalkane, because the first step in that case would be the bond between the carbon and the Br breaks up, giving Br minus and forming a tertiary carbocation, and that is the first step, which is a slow step. Then the hydroxide ion attacks the carbocation and gives the alcohol. So this is what we call the SN1 mechanism. We said this happens for a tertiary halogenoalkane, and that means that the rate depends only on the concentration of the halogenoalkane. Explain why primary and tertiary bromoalkanes are hydrolyzed by different mechanisms. Okay, let us try and explain this. Remember, if we have a tertiary halogenoalkane, we said what happens is the alkyl group in the tertiary halogenoalkanes have an inductive effect. They sort of donate electrons. So that makes the tertiary carbocation that forms when the Br leaves more stable than if it were a primary carbocation. Now the primary, we said, will not take this SN1, it will take the SN2 mechanism. This is because the primary halogenoalkane has more space for direct attack of the hydroxide on the primary carbon, while the three alkyl groups on the tertiary carbon in the tertiary halogenoalkane will prevent the hydroxide from attacking directly. This is how we explain the difference in mechanism between primary and tertiary halogenoalkanes. This next question says, a student investigated the reaction between iodine and propanone in acidic conditions. He says we have 50 centimeter cubed of 0.02 mole per decimeter cubed iodine solution measured into a flask, 25 centimeter cubed of propanone, 25 centimeter cubed of 1 mole per decimeter cubed sulfuric acid were measured. So he put iodine, and then he put propanone, and he put sulfuric acid, and several samples of sodium hydrogen carbonate were placed in separate conical flasks. The mixture of propanone and sulfuric acid was added to iodine, and a clock started. At 2-minute intervals, 10 centimeter cubed of reaction mixture was removed, added to one of the flasks containing sodium hydrogen carbonate, and the contents were titrated with sodium thiosulfate. Remember that we said this is how we do an experiment that involves iodine. Okay, so he's saying explain the purpose of adding the reaction mixture to sodium hydrogen carbonate. Of course, we said before that we add the sodium hydrogen carbonate to quench the reaction by neutralizing the acid so that the acid does not react with thiosulfate. What indicator should be used in the titration? Of course, we said if we're titrating a solution that has iodine, we use starch solution. In this experiment, the concentration of iodine was 0.02 and the concentration of propanone and sulfuric acid were both 1 mole per decimeter cubed. Why was the iodine solution used much less concentrated than the propanone and sulfuric acid? So the iodine was 0.02 while the others were 1 mole per decimeter cubed. Of course, we do this so that the propanone and the acid are in excess. Their concentration would remain almost constant through the reaction, so they don't affect the rate, and the changes in rate would be due only to changes in concentration of iodine. The shape of the graph obtained from the results of the experiment is shown below. Use the graph to deduce the order of reaction with respect to iodine. So if this is the graph that we get, that means that the reaction with respect to iodine is zero order because the gradient is constant. So the concentration of iodine does not affect the rate. In a further investigation, the different volumes of sulfuric acid, propanone, iodine, and water were mixed. The time taken for the mixture to go colorless was measured. Of course, remember that when we're titrating with starch solution, at the beginning, the starch with the iodine form a dark blue-black color. And then at the end, when all the iodine is used up, the color disappears. So that is the end point for the titration. The experiments were repeated and the results below show average values for the rate of the reaction. Explain why water is added in experiments 2 and 3. Remember that we add the water to keep the total volume constant. In order to be able to compare between the experiments, the total volume of solution in the flask should be the same. So we depending on the amounts of the other reactants, we add water so that the total is always constant. Show how you would use the data in the table to deduce the order of reaction with respect to propanone and hydrogen ions, and then write the rate equation. Okay, so let us take a look. Again, we said we have this kind of table, and he will tell you to get from it the order of the reaction. So let us take a look at experiment 1 and 2. If I look at experiment 1 and 2, the propanone is constant, the iodine is constant, and only the sulfuric acid is changing. Now, what is happening? Going from experiment 2 to 1, sulfuric acid is doubled. What happened to the rate? It also doubled. So that means that with respect to the H+, it is first order. Why? Because from experiment 2 to 1, propanone is constant. If we double the sulfuric acid, the rate doubles. Then we look at experiments 1 and 3 in order to determine the order of propanone. In experiments 1 and 3, the sulfuric acid is constant, the iodine is constant, and only propanone is changing. Now, what is happening to the propanone? From experiment 3 to 1, propanone doubles. And what happens to the rate? It also doubles. So that means first order. From experiment 3 to 1, acid is constant, propanone is doubled, the rate doubles. Okay, please remember this. Then he says he wants the rate equation. Okay, so the rate equation will have concentration of the propanone times concentration of the H+. You could either include the I2, which we said is zero order, or you could not include it if you don't want. In the rate, both would be correct. Now, this next question is about kinetics of the reaction between bromoethane and hydroxide ions. So he gives me a table and the rate equation, and he just tells me calculate the value of K. Of course, from that rate equation, you can get the equation for K. K is rate over the concentration of these two reactants. So you just take the numbers from the table. This gives you a value of K. We remember when you write a value of K, he usually asks for the units. So please try and determine the units. We said rate is mole per decimeter cubed per second. Any concentration that we have is mole per decimeter cubed times mole per decimeter cubed. Cancel whatever is the same on top and bottom. And for this one, remember the units for K changes from one reaction to the other. So for this one, it is decimeter cubed, mole to the -1, seconds to the -1. Then he says calculate the initial rate if the concentrations of both reactants were changed to 0.02. So we have this table. This is the table that we still have. But if we say he wants to change the concentrations to 0.02. So instead of 0.1 for the bromoethane, it's going to be 0.02. That means we're going to decrease it 5 times. Now the hydroxide, instead of 0.15, I'm going to make it 0.02. So that means I'm decreasing it 7.5 times. So what happens to the rate? It decreases by a total of 5 times 7.5, which is 37.5, and that gives me a value for the rate. Are we following? Okay. State the order of the reaction. Of course, if my rate equation says concentration of bromoethane times concentration of hydroxide, each of them is first order. The overall order of the reaction would be second order. The mechanism for this reaction can be inferred from the rate equation. Again, we said, will this be SN1 or SN2? Remember that if the rate equation includes both the bromoalkane and the hydroxide, that means this is an SN2 because this is a primary halogenoalkane. In that case, the hydroxide ion will attack at the same time that the Br is leaving, and I get this kind of intermediate or transition state. Remember, there is a negative sign overall on this transition state. The rate constant for the reaction between bromoethane and hydroxide ions were determined at 5 different temperatures. Here he's changing temperatures. Complete the missing values. So he wants you to calculate what is 1 over T for temperature of 333 Kelvin. 1 over T, if you calculate it, that comes out to that number. He gives me a rate constant K. What would be the len of K? Len, of course, is natural log. You get it directly from the calculator. This comes out to be this number. Then he says I need to draw a graph. So if I plot the points that he gave me in that table, this is what it looks like. And then he wants the gradient of the line. So how do we calculate the gradient? He said the gradient you should be able to calculate from the table. The gradient of a line is just the y-axis over the x-axis, and this gives me a certain number. Now from the gradient I can get the energy of activation. Remember that we said if I have this graph and I have len K versus 1 over T, then the energy of activation is minus gradient times R. Please remember that. R, of course, is 8.31, and the energy of activation that comes out from that is in joule per mole. I can divide that by 1,000, and my energy of activation can be in kilojoule per mole. Okay? Iodine reacts with propanone in the presence of an acid catalyst. Please pay attention to this. Most of the questions are very similar, so you should be able to answer them. Now, here again, he's doing an experiment with iodine. The experiment was carried out to investigate the kinetics of this reaction, monitoring the concentration of iodine. The progress of the reaction was followed by mixing together the reactants, removing samples every 5 minutes, quenching the reaction, titrating to find the concentration of iodine. So suggest a suitable reagent. Again, what do we titrate? Here he's asking for the reagent with which you could titrate the iodine. We titrate it with sodium thiosulfate. Remember, in any of these reactions, we titrate the iodine with sodium thiosulfate. State and explain how you would quench the reaction. Again, how do we quench the reaction? This is a reaction that gives out acid. So I quench it by adding sodium hydrogen carbonate to neutralize the acid. Then he gives me a table with data of time versus concentration of iodine, and he wants me to plot a graph to determine the order of the reaction. So in this graph, when you plot it, it comes out to be like this. Please practice drawing these graphs. Remember that the values for iodine were times 10 to the minus 4 or something, so you have to include that in the labeling of the y-axis. Now, from this table, order with respect to iodine, again we said if it's a straight line going down like this, then it is zero order. That means the concentration of iodine does not affect the rate. It is just used up with time. Explain how you determine the order. We said the line has a constant gradient. This is how you explain it. The rate is constant. As iodine decreases, iodine has no effect on the rate. State an alternative practical procedure that could be used to monitor the concentration of iodine. We said if I have something that has iodine, I can either do the experiment that he's talking about and titrate with sodium thiosulfate using starch as an indicator, or because iodine is a solution that has color, I can follow the loss in color or decrease in concentration of iodine using what we call colorimetry. So this follows the change in color. Then another question says bromate ions oxidize bromide ions in presence of dilute H+, and he gives me the equation. 3 experiments were carried out using different initial concentrations of the 3 reactants, and he gives me the results in a table, and then he says this reaction is first order with respect to bromate. So keep in mind that he has already told me with respect to bromate it is first order. State with reasons, including appropriate experiment numbers, the order of the reaction with respect to the other reactants. So with respect to H+, again, remember we said we choose 2 experiments in which the others are constant and only the H+ is changing. So in this case, I look at experiment 1 and 2. Now what is happening? The H+ doubles. What happened to the rate? Quadruples, that means that it is second order. We said if it doubles and doubles, that is first order. If it doubles and no effect, that is zero order. But if it doubles and quadruples, that is second order. And then you need to explain, how did we know it's second order? We're looking at which experiments? Experiment 1 to 2. What happened? The bromate is constant. The bromide is constant. What happened to the H+? It doubles. The rate quadruples. Then let's take a look at bromide. What happens to the bromide? Okay, let's choose 2 experiments in which the bromide is changing. Now, our problem here is that I don't have 2 experiments in which both reactants are not changing. Both of the other reactants are not changing. So I have to rely on the information that we already have. I know that with respect to BrO3 minus, it is first order. Now, I look at experiments 1 and 3. 1 and 3, the bromide is doubling. But also the bromate, what happened to it? It triples. We know that the reaction is first order with respect to bromate. So if the bromate triples, then the rate should triple. Now, the fact that the rate increased 6 times, that means it tripled because of the bromate, and then it doubled because of the bromide, and that means that with the bromide, it is first order. Okay? Write the rate equation for the reaction. In that case, it is first order with respect to bromate, first order with respect to bromide, and second order with respect to H+. So that's H+ to the power 2. Then he says, use the data from experiment 1 and your answers to A2 to calculate the value of the rate constant. So you have this from the rate equation. You put in the numbers from the table, and this gives you a value for K. Now, the units, again, we said rate is mole per decimeter cubed per second. Each concentration is mole per decimeter cubed. If it is H+, that means it is mole to the power 2, decimeter to the power 6. cancel whatever is the same on top and bottom, and you end up with decimeter to the power 9 mole to the power minus 3 seconds to the power minus 1. Then he says, what evidence suggests that this reaction proceeds by more than one step? Of course, we said there are 3 reactants that all are included in the rate equation, so they cannot all collide with each other at the same time. The initial rate of reaction was obtained from measurements of the concentration of bromine at regular time intervals. How is the initial rate of formation of bromine calculated from a concentration time graph? Now remember, if we have a concentration time graph, to get the initial rate, we draw a tangent at t equals 0, and we calculate the gradient of the tangent at t equals 0. Here the equation says the ionic equation for the reaction of this persulfate with potassium iodide is this. In a series of experiments to determine the rate equation for this reaction, he has sodium thiosulfate mixed with the persulfate solution and 5 drops of starch solution. He has potassium iodide mixed, and the time taken for the solution to darken. Remember that this equation, iodine is being formed, so the reaction starts colorless, and then the color of iodine with starch starts to show up. And he gives me a table and he says, explain the purpose of the sodium thiosulfate. Remember, the sodium thiosulfate reacts with iodine as it is formed. So it prevents the starch iodine color from appearing until that amount of thiosulfate has reacted, and then we start timing the rate of the reaction. Use the data in the table to deduce the rate equation for the reaction between the persulfate and iodide. Explain by referring to the data how you arrived to your answer. So we have a table and we're trying to get the order of the reaction. Okay, so which one do we start with? We can start with the persulfate. We look at experiments 1 and 2. Going from experiment 2 to experiment 1, what happened to the persulfate? It doubled. Now what happened to the time? Remember that this is time. Now the time has become half. That means the rate has doubled. When the time becomes half, that means the rate has doubled. So doubling the concentration doubles the rate, so it is first order with respect to the S2O8 2 minus. So from experiments 2 to 1, when the iodide is constant, the persulfate is doubled, the rate doubles, that means it is first order. Now with respect to iodide, I can take experiments 1 and 3. So going from experiment 3 to experiment 1, what happened? The concentration doubled. The rate also doubled because the time is half. So this is first order also with respect to the iodide. Now we need to write the rate equation. Rate is equal to K times the concentration of each of them to the power 1. A further experiment was carried out to confirm the order of the reaction with respect to the iodide ion. So he makes the persulfate with the iodide, and he has a certain initial concentration of each one. The concentration of iodine was measured at various times. Outline a method not involving sampling the mixture, which would be suitable for measuring the iodine concentrations. Remember that when we have a reaction that has iodine, either we titrate it with thiosulfate using starch as indicator, or we do what? We do colorimetry. We said iodine has a color, so we measure the intensity of the color of the iodine using colorimetry. Now, how do we explain colorimetry? We say what we're doing is we measure the transmittance or the absorbance at various times, use a calibration curve to convert the transmittance to concentration to determine the change in concentration with time. Explain why the initial concentration of the persulfate is much higher. We said when we're trying to see the effect of, for example, concentration of iodide, the other reactants should be much higher so that they remain almost constant during the reaction, and only the concentration of iodide is changing, or it is the only value. State how the initial rate of reaction may be obtained from the results of this type of experiment. Remember, when we are calculating concentration versus time and we have a graph, we plot the graph of the concentration versus time, we draw a tangent at t equals 0 and measure its initial gradient. In such an experiment, a student calculated the initial rate to be this, used the values of the initial concentrations, which he gives me to be persulfate was 2 mole per decimeter cubed and iodide was 0.025, and he says we should try to calculate the rate constant for this reaction. So this was the rate equation. That means the rate constant is rate over the concentration of the two reactants. I put in the values that he gives me and I get the value for K. For the units, again, you should know by now how to write the units. Rate is mole per decimeter cubed per second, and any concentration that we have is mole per decimeter cubed. Cancel whatever is the same on top and bottom, and this, in this case, it ends with decimeter cubed, mole to the -1, seconds to the -1. Using the method outlined in B, the rate constant for this reaction was determined. So he has a value of temperature and K, so he can get ln K and 1 over T, and we're supposed to draw a graph. From that table, the graph looks like this. Please practice drawing these graphs so that you're used to them. And usually he says we should get the gradient of the line, so that is the y part over the x of the line, and using this gradient, then I can calculate the activation energy. Remember that if I have a graph of ln K versus 1 over T, the gradient is equal to minus EA over R. So EA is minus gradient times R. We usually divide by 1,000 so that my answer is in kilojoule per mole. Okay. This next question is about elimination of hydrogen bromide from bromoalkanes by reaction with alcoholic potassium hydroxide. So he has the bromo alkane with alcoholic KOH. So this gives me the alkene. The results obtained are shown in this table, and he says explain why a large excess of the hydroxide is used. Again, why would he use excess of one of the reagents? So that the hydroxide ion remains constant, concentration of the hydroxide ion remains constant, and only the concentration of the bromoalkane is changing, or it is the only variable. Plot a graph of this from the table. The graph looks like this. So remember that V final minus VT is like measuring the rate against time. So this is changing volume against time. And he says, suggest why the value was plotted on your graph. This is because the change in volume is proportional to the concentration. So it is as if I am plotting concentration. Now measure two successive half-lives from your graph. Again, if I have this graph, how do we get half-life? We look at we said the y-axis here represents concentration. So if I'm starting with 40 to 20, I can see the first half-life from 80 to 40. Actually, it's not 80, it's 70 something. So divided by 2, that would be 30 something. So that is my first half-life. That took 2.6 minutes. So my first half-life is 2.6 minutes. And then going from 39, for example, to 19, that took 5.2 minutes. So that is a constant half-life. Remember, for this second half-life, I'm going from 2.6 to 5.2. So the difference is still 2.6. And if we deduce the order, we said if the T half or the half-life is constant, then the order is first order. In another experiment, an excess of 1 bromobutane is reacted with varying concentrations of hydroxide ions, and he gives me the table, and he says deduce the order of the reaction. Again, with respect to hydroxide ions, let us take a look at experiment 1 and 2. Now, what is happening from 2 to 1? The concentration of the hydroxide doubled. What happened to the rate? Doubled. That means it is first order with respect to hydroxide ions, and we explain that from experiment 2 to 1, when concentration of the other one is constant, hydroxide doubles, the rate doubles. That means we're first order. Write the rate equation. So the rate equation would be first order with respect to the bromobutane and first order with respect to hydroxide. Again, to get the units, we write the equation. We write the units of each of them, rate, mole per decimeter cubed, and so on, cancel. And in this case, the unit for K is decimeter cubed, mole to the -1, seconds to the -1. Another question where he gives me the table. Here he's doing 1 bromopropane hydrolyzed with aqueous sodium hydroxide and deduce the order. Again, how do we deduce the order? I want the order with respect to the 1 bromopropane. 1 bromopropane. If I look at experiment 2 to 3, the concentration of the bromopropane is doubling. What is happening to the rate? Doubling. So it's first order. And I explain which experiments, what is happening. The others are constant, hydroxide is constant, and the bromo propane doubles, the rate doubles. Now, what about the hydroxide? We look at experiments 1 and 2. What is happening from experiment 1 to 2? The hydroxide quadruples, the rate quadruples, and the other one is constant. So hydroxide also is first order from the experiments 1 to 2. The bromo propane is constant, hydroxide quadruples, the rate quadruples. The replacement of sodium hydroxide with potassium hydroxide has no effect on the results. So whether we use sodium hydroxide or potassium hydroxide, that has no effect. What does this indicate about the sodium and potassium ions in the steps of the reaction mechanism? If they have no effect, it doesn't make a difference. That means they're not involved in the rate determining step. So we call them spectator ions. They're just present there. They're not doing anything with respect to the reaction mechanism. Then this question says the halogenoalkane to bromopentane was hydrolyzed, and he gives me the rate equation. Write the mechanism for the hydrolysis of the 2 bromopentane. Now, how do I know which mechanism? Remember, we said hydrolysis of the halogenoalkane is either SN1 or SN2. Now, which one would this be? If the rate equation does not include the hydroxide, it includes only the bromoalkane. That means that this is SN1. That means we start by the carbon-bromine bond breaking to form the Br minus. This is the slow step. Remember that this happens because the carbon has a slightly positive charge and the Br has a slightly negative charge. So he's talking about relevant dipoles, so I have to include that. Then the bond breaks to form a carbocation, and then the OH minus attacks this carbocation to form the product. Okay? State how your mechanism is consistent with the rate equation. We said the reaction is first order with respect to the bromoalkane, so the slow step involves the bromoalkane and hydroxide is not involved in the slow step. The rate constant for the hydrolysis of a halogenoalkane with sodium hydroxide was measured at several different temperatures, and the results plotted in the graph shown. So he already gives me the graph, and he says from the graph determine the gradient, calculate the activation energy. So again, you should know how to calculate gradients from math. So this gradient of this line is -6290. Remember that it would differ a little bit from depending on which part you take, but it should be about this value. Then you can use that to get the activation energy minus gradient times R. And remember that we divide by 1000 so that my answer is in kilojoule per mole. Kinetics of the reaction below was investigated in a series of experiments. Compound C is a gas. A, B, and D are solutions. So he's reacting two solutions and they give out a gas. Outline a method that could be used to investigate the rate of the reaction. How do we determine the rate of a reaction in which we have a solution reacting to give a gas? I can do that by measuring the volume of gas per minute using a gas sieve. The rate of the reaction was measured at several different initial concentrations of A in presence of a large excess of the others and catalyst X. The results are shown. So just an explanation other than experimental error for the two anomalous results range. You can see that the anomalous results are the ones at high concentration. So why do you think this is much less than it should be? Well, maybe some of the product was lost before the apparatus was sealed. This would cause a greater error when we have higher concentration of reactants. What is the order of reaction of with respect to A? Remember, if I draw the rate as a straight line like this with respect to the concentration, that means as we increase the concentration, there is no effect on the rate, and that means it is zero order, because increasing concentration does not affect the rate. In a second series of experiments, further data were collected using a different method. So we have these data for several experiments. Give one reason why obtaining these further data may be considered useful. So he has more and more data. This is to increase the reliability of the results. State the order with respect to B, and hence deduce the order with respect to X. So let's take a look at B. I want to determine the order with respect to B. I choose experiment 1 and 2 because A is constant and X is constant. So what is happening to B? From experiment 1 to experiment 2, it's tripling. Now what happened to the rate? The rate increased 9 times, and that means we're talking about second order with respect to B. So from experiment 1 to 2, X is constant, B is triple, the rate increases 9 times, and that means it is second order. If we look at X, what is happening with X? Okay, well, I need to take experiment 1 and 3. So from experiment 1 and 3, X is doubled. A is constant, so it will not affect anything, but B is quadrupled. So what happened to the rate? Remember, we said it is second order with respect to B. So if B quadrupled, then the rate should increase what? It should increase 16 times. Now, when X doubled, the 16 doubled also. That means that X is first order. Are we following? We're looking at experiment 1 and 3. B quadrupled, and it is second order. So if it quadrupled, that means 4 to the power 2, so it's 16. So my rate should increase 16 times. Now X doubled, so the rate also should double. So instead of 16 is 32. So that is first order with respect to X. And you should write the explanation that we're talking about. Use your answers to give the rate equation. Of course, in that case, this would be my rate equation. Use your answer and the appropriate data from experiment 3 in the table to calculate the value of the rate constant K. So K would be the rate over these concentrations. I put in the numbers. He wants experiment 3. Please use the values that he wants. This gives me a value for K. Now, the units, well, the units would be mole per decimeter cube per second for the rate, and each of the concentrations is mole per decimeter cubed. Of course, if it is to the power 2, then it's mole to the power 2, decimeter to the power 6. Overall, when we cancel what's the same on top and the bottom, it is decimeter to the power 6, mole to the power minus 2, seconds to the power minus 1. A student carried out an experiment, an investigation into the kinetics of the reaction between bromopropane and hydroxide ions. A summary is shown of the mechanism, and he says, use your knowledge of the mechanism of nucleophilic substitution reactions to suggest two features of this summary, including the student's mechanism, that you think are correct and two features that are wrong. Can you see the mechanism that he gives? Give two things that are correct, two things that are wrong. What is correct about it? The mechanism involves formation of an intermediate. Yes. So this is correct. We need an intermediate. Both OH minus and bromoalkane are involved in the slow step. But what is wrong about this mechanism? The direction of the arrow of the hydroxide ion, the curly arrow, should be from the hydroxide to the carbon, not the other way around. And the bonds in the intermediate should be partial bonds, not complete bonds. We draw them with dots. They are partial bonds. Okay, this next question, very similar. A student investigated kinetics of the reaction that is given. He gives me a table and he says determine the order with respect to the peroxide and H plus ions. Again, let us take a look at this. This is the table. If I'm talking about the hydrogen peroxide, looking at experiment 1 and experiment 2, the H plus and I minus are constant. Now, what's happening to the H2O2? It is doubling from experiment 1 to experiment 2. What's happening to the rate? Doubling, then it is first order with respect to H2O2, and we explain. What about H plus? Well, we take a look at two experiments in which the H plus is changing, the others are constant. From experiment 1 to 3, the H plus is doubling. What is happening to the rate? There is no effect on the rate, and that means it is zero order with respect to H plus. Do we understand this? The student carried out 3 more experiments and he draws the graph. State the order with respect to iodide. If we have the rate increasing as iodide increases, this is first order. So concentration of iodide increases, the rate increases, and it is directly proportional. Then we said use your answers to write the rate equation. Okay, so we said first order with respect to this, first order with respect to the iodide. Use the data from the table and your answer to A3 to calculate the value for the rate constant. So the rate constant, I want experiment 1, for example. Then I can put in the values for the rate and the concentrations from experiment 1 and I get this value. I want units. You should be able to get the units by now. Then the next question says nitrogen dioxide reacts with carbon monoxide in this equation, and he says the reaction is second order with respect to nitrogen dioxide, zero order with respect to carbon monoxide. Suggests a possible two-step mechanism. Now, if he says it is second order with respect to nitrogen dioxide, that means my rate determining step has to include 2 moles of NO2. Then zero order with respect to carbon monoxide, that means the carbon monoxide is not in my rate determining step. So these are 2 possible mechanisms that you can write. Either you start with 2 moles of NO2 to form N2O4, and then the N2O4 reacts with the CO, or 2 moles of NO2 break up to form 2NO plus O2, and then the O2 reacts with the CO. So remember that the rate determining step cannot include CO because it's zero order with respect to CO, and it has to include 2 moles of the NO2. This question says crystal violet is an indicator which is colored in solutions of acids and colorless in alkanes. The kinetics of the reaction of crystal violet and sodium hydroxide were investigated using the abbreviation CV plus for the formula of crystal violet. A simplified equation for the reaction is this: equal volumes of 0.1 mole per decimeter cube sodium hydroxide and 5 times 10 to the minus 5 mole decimeter cube of crystal violet. So the concentration of the crystal violet is much smaller compared to the hydroxide. Explain why very different concentrations were used. Remember, we said we use a very large amount of the one we are not testing. So hydroxide, for example, I'm trying to determine the rate with respect to crystal violet. So I keep the other one very large so that it's almost constant, and only the crystal violet concentration will affect the rate. So just a method which could be used in this experiment to continuously monitor the change in concentration. Remember that he says it has different colors, so I can use colorimetry. Okay? The graph shows how the concentration changes with time, and he says measure 2 half-lives. So again, how do we measure the half-life? We're starting from 2.5, so I go from 2.5 to the half of that, which is 1.25. How long does it take? It takes about 7.5 minutes. And then I go to the next half-life. So the first half-life is 7.5 minutes. I go to the second half-life, so that is from 1.25 to 0.75. And that takes also about 7.5 minutes. And that means that my half-lives are constant, and that means I'm talking about something that is first order. In another series of experiments, the rate constant was determined at different concentrations, and he gives me the table. Now complete the table by calculating the missing values. So the missing value is just 1 over t. So the t is 297. I calculate 1 over t. Len k, he gives me the k, and I get the natural log of that. And then he wants me to plot a graph. Please pay attention to all the different types of graphs. So this is the other different type of graph where we're plotting len k versus 1 over t. Remember that the 1 over t is very small number. So in my case, I put it times 10 to the minus 3, or you could just put it 0.0033, whatever. The len k is a negative value. That's why we have going down in the y-axis. We plot the points from the table. We get the gradient of the line. Please show him how you got the gradient, which parts you used. The gradient in my case here is this, and it comes out with a negative sign. Please do not forget that len k is negative. So the line is a negative gradient. And then I can use this gradient to get the activation energy. We said activation energy is minus gradient times R, so that cancels the minus that we had for the gradient. Divide by 1,000 to get your answer in kilojoule per mole, because the R is 8.31 in joules. Okay. The next question is talking about bromate ions reacting with bromide in acid, and he gives me a table of different experiments, and he says the reaction is first order with respect to bromate. Now deduce the rate equation. So of course, to get the rate equation, I have to determine the order with respect to bromide and the order with respect to H+. So let's take a look at this. If I look at experiment 1 and 2, the bromate is constant, bromide is constant, only the H plus is changing. Now what happened to the H plus from experiment 1 to 2? It doubled. What happened to the rate? It quadrupled. That means second order. So the reaction is second order with respect to H plus, and you explain what is happening. Now with respect to the bromide, I can look at experiment 1 and 3. He already tells me that it's first order with respect to bromate. So the bromate increased by 1.5, so my rate should increase by 1.5. But the bromide increased by 2, so that 1.5 will increase also by 2. So it is first order with respect to bromide. Experiments 1 and 3, the H plus is constant, the bromate increases by 1.5, and it is first order, so the rate should increase by 1.5. But it increased by 3 times. That means it also increased twice like the bromide, so the bromide is first order. So that would be my rate equation. Concentration of bromate to the power 1, bromide to the power 1, H plus to the power 2. Use the data to calculate the rate constant. So the rate constant is this. I put in the numbers. He wants experiment 4, so I have to use experiment 4. I get a value for K, determine the units. Again, in this case, it will be decimeter to the power 9, mole to the power minus 3, seconds to the power minus 1. Give one possible reason why the rate equation shows that the reaction cannot proceed in one step. Again, we said if I have several reactants, if they're just 2 reactants, they can happen in one step, theoretically. But if I have many reactants, then there is a large number of particles in the reactants that cannot all collide at the same time. So it has to happen in more than one step. This question is talking about decomposition of benzene diazonium chloride in a first order reaction, and he has a table of time versus concentration at a certain temperature. So this is at a temperature of 333 Kelvin, and he says plot a graph of the concentration versus time. When you plot the graph, you will find that it looks like this. Please take time to sit down and try and draw the graph on your own so that you can practice. Determine the half-life. How do we determine the half-life? We take a look at one concentration and divide it by 2. So in this case, if I take from 0.3 to 0.15, how long did it take? It took from 95 seconds to 215 seconds. So my half-life is the difference between them, that is 120 seconds. Calculate the rate constant. Remember that we said for a first order reaction, the rate constant will be this expression of ln2 over half-life. So K is ln2 over half-life. Ln2 is 0.693 if you do it with a calculator. The half-life we got is 120, so this is my value for K, and in this case it has a unit of seconds to the minus 1. The experiment described in A was repeated for 5 temperatures. Now use the rate constant that you calculated to obtain the data for 333K. Remember that he was using 333K in the first part of the experiment. So we use it to get len K. Len K, we already calculated K, and len K in this case is minus 5.15. This is at 333K. So I want 1 over T. 1 over T is 0.003. I plot the point and I draw the graph. Okay. From this, we determine the gradient. Again, we should know how to get the gradient of this line, and it is the part in the y-axis over the part on the x-axis, and this gives me a value in negative because len K is negative, so this is a negative value. Okay. The units in this case for the gradient would be K, because len K has no units, and the x-axis is k to the minus 1, so this overall unit is. Use the gradient to calculate activation energy. Again, activation energy is minus gradient times R. We divide by 1000 to change it to kilojoule per mole. I hope these questions are getting easier as we go on because they are very similar to each other. The hydrolysis of halogenoalkanes by alkali is a nucleophilic substitution reaction. The mechanism for this reaction for primary halogenoalkanes is different from tertiary. Describe how knowledge of the rate equation for the hydrolysis provides evidence for the mechanisms. Again, would this mechanism be SN1 or SN2? Remember that we said if I have a tertiary halogenoalkane, the mechanism is SN1. Now, how do we know that? The slow step is the first step in which the X bond is broken to form a carbocation, and that means that the rate equation involves only the concentration of the halogenoalkane, not the hydroxide ion. So he's saying how the knowledge of the rate equation will determine the mechanism. So if the rate equation is equal to K times concentration of our X, that means it is only first order with respect to our X, and that means it is SN1. But for a primary halogenoalkane, we said the mechanism is SN2. And that means the initial slow rate determining step involves hydroxide ion attacking the halogenoalkane to form an intermediate. And the rate equation would involve both the halogenoalkane and the hydroxide ions. Then I know that this is an SN2 mechanism. A student investigated the kinetics of this reaction, again bromate with bromide with H+. Notice that this kind of reaction is repeated many times. In the first experiment, the student measured the initial rate of the reaction at 5 different concentrations of bromate ions, used the results to plot a graph and show that the reaction is first order. Okay, so we said when we plot the graph of rate versus concentration of bromate, we find that it is a straight line going from 0 up. This means it is directly proportional, and that means that this is first order. So as the bromate concentration increases, the rate increases. It is directly proportional. That means that it is first order with respect to the bromate ion. In the second experiment, the student determined the rates of the same reaction with different concentrations of the reactants. So we want to determine the order with respect to bromide ion and H+ ion. So which experiments can I use? Experiments 1 and 3, the bromate is constant and the H+ is constant. So looking at the bromide, what happened to the bromide? It tripled. What happened to the rate? Tripled. That means it is first order. Now the H+ ion, what happened to the H+ ion? Well, the only experiments that I have are the ones that has experiment run 1 and 2, in which bromide is constant, but the bromate changes. And we know that it is first order with respect to bromate. We already got that from the previous graph. So what happened to the bromate from run 1 to run 2? It is increasing 5 times. So the rate should also increase 5 times. But then the H+ ions decreased by half. So what happened from 1.52 to 1.9 times 10 to the minus 5 is that it increased 5 times because the bromate is first order. But then it decreased 4 times. Instead of decreasing half, it decreased 4 times. So that means it is second order with respect to H+ ions. And that means the rate equation is this. First order with respect to bromate, first order with respect to bromide, second order with respect to H+. Use the results for run 1 to calculate the rate constant. So you put in, for run 1, you put in the values for K. You also determine the units. As we said before, it will come out to be decimeter to power 9, mole minus 3, seconds to the minus 1. The presence of bromate ions in drinking water is harmful to humans. Bromate ions can be converted to less harmful bromide ions by passing the water through palladium with a reducing agent. Describe how a heterogeneous catalyst, such as palladium, increases the rate of reaction. Remember, we said there are homogeneous catalysts in which the catalyst is the same state as the reactants. If the reactants are in solution, the catalyst is also a solution. But for heterogeneous catalysts, we said the catalyst is a different state from the reactants. So if the reactants are solution, the catalyst is a solid. So how does this work? We said the reactants are adsorbed onto the surface of the catalyst. This weakens the bonds in the reactants and the reaction occurs. Then the products are released from the surface of the catalyst. So please remember how to explain the heterogeneous catalyst. This question is talking about bromide reacting with bromate and H plus ions, and he says the concentration of bromide ions is determined at different times, and the others were in large excess. So we said the others are usually in large excess, so that the only variable here would be the bromide ion, and he gives me the graph already of bromide versus time. And he says determine the order of the reaction with respect to bromide ions. Now, how do we get this? We get from the half-life. If the half-life is constant, then it's first order, remember. And then we said here, what is the half-life? From 0.1 to 0.05, it takes about 200 seconds. Can you see that? And from 0.05 to 0.025, it still takes from 200 to 400, so it's the same 200 seconds. So the half-life is constant, and that means it is first order with respect to bromide. The initial concentration of bromate and H plus are changed, and the initial concentration of bromide ions is constant in large excess. Determine the order of the reaction with respect to the bromate and the H plus. So what do we do again? Look at two experiments in which the other one is constant, and then we look at the one that is changing. So from run 1 to run 2, the bromate doubles, H plus is constant, the rate doubles, and that means it is first order. Now, to get the H plus, we look at from experiments 1 and 3. Now, experiments 1 and 3, what is happening? In experiments 1 and 3, the H plus doubles and the bromate triples. And what happens to the rate is that it increases 12 times. So that means that the H plus must be second order, because if the H plus doubles, then the rate quadruples, and that is tripled because the bromate is tripled, so that is increasing by 12 times. So H plus ions is second order. Give the overall rate equation. Again, this is the overall rate equation. Include units for the rate constant. So this would be the rate constant, and this would be the units. Are we following? Is this getting much easier? Okay. Rate constant for the reaction between bromoalkane and cyanide ions is determined at different temperatures. Plot a graph of len K against 1 over T. Use it to determine the activation energy, sign and units of gradient and activation energy. So let's draw the graph. If we draw the graph for that table, and then we get the gradient, and we should know that the gradient is a negative value. Activation energy would then be negative of that gradient times R. Divide by 1000 will give me the value of activation energy in kilojoule per mole. Okay. Thank you for listening. I hope this was not too long, and I hope that now the questions on kinetics are much easier. Thank you for listening.